So I'm going to get a drawing up here to refresh what we've been doing. Do a quick review. Okay, so let's review what we were talking about last time on the double slit. What we are trying to do is determine the intensity pattern on a distance screen from light illuminating a double slit apparatus and find out what the intensity of the light is as a function of the angle from the center. So in short, what we want to know is what is this intensity I of theta? We derived last time where the maxima and where the minima occur. We know what the conditions are where the angles of maximum intensity occur. They occur at d sine theta equal to m times lambda, where m is equal to 1, 2, 3, etc. Right? And this is for intensity maxima. And we call those maxima fringes. And I probably drew this a little bit incorrectly here, so let me do it a little bit better. So we basically are looking at, for example, m equals 1, m equals 2. So this would be m equals 1. This would be the intensity maximum for m equal to 1. This is also the intensity maximum for m equals 1 because it's the same dynamics or light pattern or optics. And then this one would be, for the second one from the center, would be m equals 2. And the condition that occurs is we could actually write that, for example, we could put sine theta. Let me rewrite this a little bit. So let's call this sine theta m for the nth maximum. And then I'm going to put in parentheses max, because I want to emphasize that this is the angle for which I see the maximum intensity, and it occurs when d sine theta is equal to m lambda, and of course, as I just said, m is equal to an integer, which is 1, 2, 3, etc. Right? So what we want to do is, we know where the maxima and the minimum are. The minima occur halfway between the maxima. We had an equation for that last time as well. But what we want to know in general is, how do I describe this intensity function as a function of theta? So if I to show you a picture of an actual intensity pattern from a double slit, let's see if I can find it here. There we go. We've seen this before on the slides, but we'll bring it back occasionally. Then what I'm looking at is, this is the intensity pattern from a single slit, right? So the light is coming in front of the projector, or I'm sorry, in front of the screen. There's a single slit. The light diffracts through the slit and the vertical slit, and I see these patterns of maximum, minimum, maximum, minimum, maximum, minimum. So we're looking at this oscillatory behavior of the intensity as a function of the distance from the center, or as we can describe also the angle from the center. So remember last time we said that we could describe, I'm sorry, this was the single slit. This was the single slit pattern, but nevertheless, it still shows that you have a central maxima and you have intensity patterns that are actually, in this case, dying out as you move away. But the same is true at the double slit. I don't think I brought a slide up with the actual picture of a double slit. This is actually a single slit, but the phenomena is still the same. And what we're doing is trying to find out how to measure the intensity across a line that you draw perpendicular to these slit patterns. So this intensity I of theta that we're trying to derive, we said last time, we're going to use a property of Maxwell's equations that says that the intensity of the light on a distant slit is proportional to the magnitude of the electric field squared. So last time we wrote down an equation for the magnitude of a oscillatory electric field, and which is part of a light wave, and we could write that E theta is equal to E theta 0 times sine of kx minus omega t, for example, right? And this is a sine wave that is propagating along the x-axis. And E theta 0 is the amplitude of the sine wave. Right? Now, in the case, and of course theta, it'll be a function of theta because we know the intensity changes as a function of theta, and we need to know what that is. But in our case, what we had been talking about last time is that the electric field amplitude for this particular example is one where we are adding the electric field, let's say, for a traveling wave E1 and another traveling wave E2. And because of the fact that this wave travels a larger distance to this point than this wave, there will be a path difference between those two. And that path difference is equal to, this segment right here is equal to little d times sine theta. Right? That's a path difference. And one of the things we've been discussing is that if I have two waves in which one goes a slightly different path, length, than the other, and as a result, you can see here that this wave will arrive at point P before this wave does because it has a longer time to go. So there will be a phase difference between these two waves. So when they arrive here at this point, I'll have the electric field, let's say from E1. Let's see if I can, so the electric field from, or let's say, yeah, from E1, and it will look something like this. And the electric field from E2 will have a phase that is slightly displaced with respect to the other one. And so it will have a sine wave that looks like this, right? And they are somewhat out of phase. We say we can call this phase difference between these two waves a phase difference that is equal to delta. Delta is the phase difference between these two waves. Furthermore, we said last time that we can say that generally when we're adding two waves together, that if one travels a path difference, there's a path difference between the two waves before they arrive at a distant point. There's a path difference between two waves, I'll say the two waves. Then if I multiply this by the conversion factor 2 pi over lambda, then that gives me the phase difference. We call this delta, and this is the phase difference between the two waves. Now, we said last time that if the two waves are in phase, that is to say that delta is equal to 0, then when we add up the amplitudes of these, the resultant amplitude of the waves E1, E2 will simply be, the resultant amplitude will be E1, 0 plus E2, 0, where this is the amplitude of the individual waves. And I get a wave that's twice as high. For example, when, in the case we'll be looking at, that E10 is equal to E20. So we'll just say this, make a shorthand on this and call this equal to 2E0. On the other hand, if the phase difference delta between the two waves is 180 degrees, right, then the two will subtract from each other, and I will get that the resultant electric field wave will be equal to 0 everywhere. Everywhere. They cancel, right? So depending on the phase difference, I can get a superposition that doubles the amplitude when I add the two waves together, or I can get a superposition of the waves that cancels and goes to 0. In general, delta is not equal to 0, which is, or it's not equal to 180 degrees, right? So the next question is, since I obviously know how to calculate the intensity for those simple cases, what is the intensity when I'm looking at another point P and off at an angle theta? So I want to derive or explain the shape of this curve, right? As I move away from the center. These are the shape of the intensity of the, we call these the diffraction peaks? The interference peaks, I guess these are called. These are called the interference peaks. So we want to look at the shape of those. Now, how do we do, so where are we heading with this? Well, what we need to know is that when I add these two waves together, they will, remember, they will in general be phase shifted from each other because one travels a distance d sine theta further than the other one. So when I add them together, I'm adding two waves that have a phase difference between them. And I will expect then that there will be, I'm trying to think, read this one. That the superposition of these waves, and let's see, I wish I had a third color. Unfortunately, I got delayed in getting here today, so my third color is not available. So we'll say that this represents the superposition of those waves, and this is E theta, and this amplitude is E theta 0. This amplitude is E theta 0. I get a new amplitude, right? So here's the route to finishing the problem. If the intensity is proportional to the square of the amplitude of the resultant wave, when I add two waves together that are displaced in phase from each other by a certain amount, I will get a new amplitude E theta 0 squared. Once I'm able to find that as a function of the phase difference, then I can calculate the intensity as a function of phase difference. And phase difference is also a function of angle because the path difference, we said, between the two waves is d sine theta. So d sine theta times 2 pi over lambda is equal to delta, the phase difference. Right? And this is generally a very powerful equation. You'll see this used as something you will want to use in problems, homework problems, or understand the theory that path difference times 2 pi over lambda equals phase difference. Right? It's a very useful expression to remember. That's one of the generally hold. Sorry, cell phone's off. Cell phone's off. Anyone else forgot that? Okay. So that's the general route that we are going to follow. So now the question is, how do I calculate how to get E theta 0, right? And this is the sum of two sine waves that are of different that are off in phase from each other by some small amount. Okay. So how do we get there? Okay. Once we're able to get that, then once we get E theta 0, then we can calculate the intensity as a function of theta, right? And that's the answer that we're after. How does the intensity change as a function of angle from the central maximum? So let me see if I can find one here. I went down too far. So we were at this one. Okay. So this is the general approach we're going to take. There's a theorem that uses what's called the phasor diagram. And the theorem says that if I want to find the amplitude of the resultant summation of those two waves that are separated by some phase difference delta, then I can do that, the amplitude of the resultant field, which is E theta 0, of the resultant field is given vectorially given by the length of two vectors added together. The length of E1, a vector we'll call E1, and a vector and E2, I should say plus E2. E1 plus E2 is given by the length of vector of the vectorial sum of E1 plus E2. So that is, and how do I write that? The way I write that is, let me draw out a vector which is the electric field amplitude from the light coming from slit 1, and I'll call that E10 for that amplitude. And now the other one that I'm adding to it has a phase difference delta. So remember, delta is the phase difference between the light arriving from at point P from one versus the other. And this is the length vector of the electric field amplitude from the second slit. And if I add these two together, then vectorially, then the length of that vector, I'll try to make this a little bit easier to read, then the length of that vector is what I want. This is called E theta 0, okay? So the way I get the resultant amplitude of two sine waves added together is to make a vectorial addition of the two amplitudes individually, but describing them vectorially with a phase difference delta or an angle delta which corresponds to the phase shift between the two waves. So it's this length that I want. This length is now the resultant, right? Now let's think about that for a couple simple cases. Supposing that delta is equal to 0, there's no phase difference between the two waves. Then the two waves are adding in phase together, so I should, if delta equals 0, then the resultant amplitude of the wave will be simply E10 plus E20, and this will be the resultant amplitude E theta 0, right? They add together linearly, and they double if if they're equal amplitudes, then we've doubled the net amplitude of the wave. When there's no, that's what we expect. If the phase difference between the two is 180 degrees, we expect that the maxima of one wave will cancel, the minimum will arrive at the same time as the minimum or the trough of the other wave, and the two waves will cancel, and we should get E theta when delta is equal to 180 degrees, we should get that E theta 0, the resultant one, is equal to 0. And sure enough, if I draw out E10, which was the amplitude from the first wave, and it is out of phase with the other one, E20, then the vectorial sum of these two is equal to 0. So the phasor diagram seems to have, we're not going to prove that here, but it seems to be reasonable that as the phase difference between the two waves increases, the amplitude decreases. This vectorial length gets shorter and shorter as the delta increases, right? So it's the length of this vector that we're after. And the length of that vector is the amplitude of the sum of the individual waves. So when we do that, then what we are ultimately after is intensity is equal to a constant times times the square of the electric field amplitude E theta 0 squared, right? So let's calculate E theta 0 squared, and then we're done. Then the problem is solved. Because once I've got E theta 0 squared, I can now see how intensity varies as a function of angle. That's the goal. The goal is to find out how does the intensity vary. So this diagram on the board is way too complicated. I mean on the slides, but you know I put it there because it does have the two vectors. It's just that omega t is not relevant here. What is relevant is there are two equal length vectors that are separated by, differ by an angle delta, the phase difference between the two, and that's going to generate a difference in the or a change in the amplitude of the two waves added together. Okay, that's a long-winded 25-minute speech, so this is the time to stop and ask a question. Things are making sense. I'll pause. Is everyone following this? Anybody? Okay, so if people, now I won't necessarily stop and ask questions, but how many, does this make sense? Am I speaking a foreign language up here, or does this seem like, yeah, that you can kind of follow the thread? Yeah. So I mean, part of that is spending some time thinking about it. You know, all I can do is provide the introduction up here and a little bit of guidance, and then of course the rest, as they say, is up to you guys. You know. And some help, of course. Okay, so that's where we're at. Okay, so how do we solve this problem? Let's see. So the basic problem that we need to solve is what is that length of that vector E theta 0? That is the amplitude of the resultant wave when I add two sine waves together of the same frequency and wavelength, and in this case the same amplitude. I guess I don't need to erase this part, do I? Yeah, maybe I better pull this out. Okay, so how do I get the length of that vector? Well, it's actually pretty straightforward. Let me draw it in a different way. Let's draw the first vector horizontally. And the first pen bites the dust. So here's the first vector horizontally. Then I have the second vector. And then I have, of course, what I'm looking for, right? So basically, the basic idea is that using some simple geometry formulas, we'll go into here, and this is a rhombus, so we can make a parallelogram and so forth. You can show that this angle is actually the same as delta over 2. All right? Now, okay, once you do that, and I'm going to call this amplitude E0, and I'm going to call this amplitude of the second wave E0, and there's a phase difference of delta between the two sine waves, right? And so I want to know the length of this. Well, that's pretty easy now because half the length of this right here, using drop a perpendicular, use a trig function, and I get that this leg, this half of it is E0 times cosine of delta over 2. Right? Similarly, this side is also equal to E0 times cosine delta over 2. So the total length of the vector, this length right here, which we call E theta 0, the amplitude of the sum of the two waves is given by 2 times E0, the amplitude of the individual waves, times the cosine of the phase of half of the phase shift between them. Okay? And really that's the only result I need to finish the derivation, is that The resultant amplitude, when I add two waves together of equal amplitude, and of course the same frequency, but differ by a phase difference delta. So delta is the phase difference, and we said the phase difference is 2 pi over lambda times the path difference, and the path difference is d times sine theta. Okay, so that's the equation we have. We are now ready to finish the solution, right, by using the intensity equation. Remember, to find the intensity as a function of theta, I have to find the electric field as a function of theta. That's what this is. This gives me the electric field amplitude as a function of theta, and it's changing because delta is changing, because I'm going to a different point on the screen. Okay, so how do I calculate this? Okay, so I take that the intensity as a function of theta is given by a constant times the square of the resultant electric field amplitude, so it's E theta 0 squared. So I square this and put it in here, and it is given by 4C E0 squared times cosine squared of delta over 2. Okay? Now this whole thing in here is a constant, right? C is some constant. In fact, I think we stated earlier in the slide that it can actually be written as epsilon naught times C, where epsilon naught is the electric permeability of free space, and C is the speed of light. But for us, it doesn't matter. It's a constant, all right? It's some constant, right? And it's going to get folded in with E0 squared in any case, right? Okay, so now, how do I get rid of this constant? Well, if I only care about expressing the intensity as a relative to the central maxima, right? So remember what the central maxima, let's see if we have somewhere I had here a double slit intensity pattern that we came at right here. Let us say that here's our double slit intensity pattern going off at an angle theta from the slits. Then I can express the intensity at any other angle except relative to the angle at theta equals 0 by solving this equation at theta equals 0. So let me do this and say what happens when I have, if I want to evaluate this at theta equals 0, so I would write that the intensity at theta equals 0 is equal to 4C, constant C, times E0 squared. Now, the reason, and this term, cosine squared delta over 2 is equal to 1. Why? Because when theta equals 0, up here, delta equals 0, right? Theta equals 0, sine theta equals 0, delta equals 0. Cosine of 0 is 1, right? So evaluating this at theta equals 0 just says that this whole thing out here is simply the intensity at theta equals 0. So now I can say that the intensity as a function of theta is equal to we call it I sub 0, which is this quantity. We'll call this I sub 0, the intensity at theta equals 0, times cosine squared of delta over 2, and delta is equal to 2 pi over lambda times d sine theta. Okay? So I now have the intensity as a function of theta, which follows a cosine squared function. So this function right here that you see up here, actually the minima should actually touch the vertical axis because the intensity really does go to 0. But it does map out what we would call a cosine squared theta function. Right? And that's the intensity pattern for a double slit. And we have derived that, and it has been compared with experiment to show that the assumption of adding two waves together will in fact produce the intensity pattern that we expect from classical electromagnetic theory. And it works, So we say, great, you know, light acts like a wave. We just proved it. Okay? We've taken a measurement, compared it to the theoretical aspect of this curve, and we get a result that says, this is what we have. This agrees with experiment. I'm trying to see if I have another one up here. This is also a double slit experiment, but the size of the peaks decreases as you move away from the central maximum. We will get to that in the next week to explain why that is true, but still, it's still a cosine squared theta distribution, which is oscillatory. It goes up and down, up and down, up and down. For the one that we just derived, if we plotted this out, we would see this function. We would see this sort of cosine squared function, and of course the amplitudes do not die out as you move away from the central axis. And that's exactly what this derivation tells us, that as I continue to go out in theta, then this thing will oscillate many times, but the maxima will always occur back at the same value as the central intensity maximum. Okay, any questions so far? That's a lot to get through.
No question.
What's that? Yeah.
What happens if your two light lengths are different?
Oh, well, I mean, first of all, if the wavelengths are different, there will not be, you will not have a constructive interference if you average over many wavelengths. So you will not see an interference effect if the wavelengths are different. Now, you can have two wavelengths going through both slits, and we showed that last time, like if you have white light going through both slits, then I can have green, red, blue, and orange all going through the double slits, and I can look at them individually. I can look at where are the peaks for the blue, and where are the peaks for the yellow, and where are the peaks for the green. But if I had yellow from one slit and blue from the other slit, I don't think you would see an interference or a diffraction pattern that's oscillatory. I think there would be an absence of any interference effects like we've seen here. But I haven't looked at it. I have to think about that. And you will not have a question on that on your opinion. However, there is a homework problem where you have to consider what if the light intensity for one slit was larger than the light intensity from the other. We worked out the case where E0, where the amplitude of the light from one slit is the same as the other. And that was fairly straightforward. If these two amplitudes are different, then you have to use the law of cosines to calculate the length of the resultant vector. Okay? And if you forgot the law of cosines, then go look it up on Wikipedia, which is what I did. Because the last time I derived the law of cosines was 1968, and that was probably before even most of your parents were born. Or maybe it was about the time you were born. No, 69. I'm sorry, 69. No. But who's counting? Okay, so everyone see that? That's sort of clear? Yeah.
In the textbook, it was like there was an equation like that, but it was saying like E over 2. So does it not matter whether we call it like delta or E?
The equation of what are you calling E over 2?
Like they were calling the phase difference like P, I think, or phi.
They do have a different notation in the book, so I have to tell you that my notes and my lectures are based on Jean Coley. By the way, there's a copy of Julie Coley on reserve in the Faraday Library. In Faraday Hall, the Math and Physics Library. You can look it up. And I believe that, so Jean Coley, my angle delta is his angle alpha, I think. I forgot. He calls it a different name. So, and he doesn't use the phasor diagram. I like the phasor diagram to give you the resultant vector. He uses trig identities, right? Which I think is, I mean, it's sort of the same, I guess, but I just like the phasor diagram better. And we're going to use it again when we do single slit. Any other questions? Okay, so this is our first result, and so we will do some. We did this problem last time. I'm sorry I don't have more time for problems. I will try to do a few more as we go through the next section. You know, one of my biggest complaints is that this needs to be a 4-hour course and we need to have a recitation, but so far we've not been able to do that. So let me see if I'm where I'm at here. Yeah, so this is the result. So the result of our derivation is that the intensity is a function of cosine squared delta over 2, and delta over 2 can be written in terms of the angle theta. Okay. So I think we've got a good result. Oh, very good. And if we plot out the intensity as a function of theta, there's the real cosine squared term. So this is actually the intensity as a function of theta from the double slit. Now, it is true that as you go further and further out, these intensities will drop off because your light source is further from the slit, and these peaks will get smaller and smaller as you go out. We will also see a case of that when we do single slit diffraction in the next section. So that's just a plot of and you can study this on your own. These slides are all online. One more point about diffraction, which is the bending of light around an object. Instead of having a slit or a hole for light to go through, I could have the solid disk with light that can only travel around the disk. So this solid disk actually blocks the light, but light can arrive from any point at the same vertical distance from the disk to the screen. And what you can see is that the light from for every point of origin of light above the disk, there's a point of origin of light below the disk, which we call the wavefront, and it will travel the same distance to the central spot as a point of light from above the slit. Consequently, those two waves will add in phase, and there will be a bright spot because the amplitude of the wave has in fact doubled. As I move further away, if I move up further away on this side, there's a corresponding point on the other side that also travels the same distance to the central spot, and those rays will add constructively, and et cetera, as you go further and further out. So the summation of all the light rays at the central spot should in fact be bright if we have a diffraction pattern. And experimentally, if we look at the light intensity pattern at the center on the screen that is located in line with the center of the opaque disk, there's a bright spot right here. You see this bright spot? And that really does show up. Furthermore, notice you do have rings of intensity maxima, minima, maxima, minima, maxima, minima. So this oscillatory behavior of the intensity pattern can also be seen when we have a central disk as well. Now, to finish the rest of the physics of this chapter, what we're going to look at is what is the intensity pattern we get from a single slit. So this one right here that I was referring to before really is the intensity pattern from a single slit. It does have maxima, it does have minima, and in this case, this central maxima is much larger than the maxima as you move away, or we would say the fringes, which are these locations of high intensity away from the central maximum. So we want to apply the same idea, wave theory of light, that we did with the double slit, apply it to the single slit, and produce a intensity pattern as a function of angle or a function of distance. Since angle and distance are related, the angle is just the sine, the tangent of the angle is the distance divided by the the distance to the screen. So we want to be able to describe what is the intensity as we move across the screen. And we want to use the same sort of logic that we did for the single slit. Right? So how do we do that? Well, the way we do it in this case is that the way we're going to do it, I need a drink of water. Well, the way we're going to do it is let's take that single slit, and you see that I have multiple rays that I can draw that are going through that slit. And effectively what I'm doing is I'm taking the single slit and I'm dividing it up into subslits. Right? So in this case, if I look up here, I have 1, 2, 3, 4, 5, 6, 7 rays. So imagine that the light is coming from 7 subslits. So imagine I have a thin partition between every seventh of a width of the slit, every seventh of a lip, and I put a small septum in there that basically breaks this single slit up into 7 individual subslits. And now I have rays that are coming from the subslits. And so what I can do is to say, what is the intensity pattern going to look like on a distant screen as a function of theta if I break it up into 7 subslits? Of course, if I break it up into 10 subslits, it'll be more accurate. If I break it up into 30 subslits, etc., and the limit that the number of subslits goes to infinity, I do a calculus integral and I find that the actual true number, because we go to the limit of infinitesimal subslits, and then we get the most accurate answer. All right? So, but we look at it conceptually. We start with 7 because that's easy to draw on the board, and I can point to a picture and tell you what we're looking at. Okay, so let's look at what the intensity pattern would be at theta equals 0. So imagine that there's a distant screen. Ignore the 3 figures to the right of the first one, and there's a screen at a distant point, and we're looking at the intensity at the point theta equals 0, where all these rays converge. Now, notice that the rays don't converge in the picture. They're shown as parallel. Why? Because if the distance to the point is very, very far compared to the dimensions over which the light can pass through, then essentially when we're calculating path differences, all of the path difference can be considered by treating these as parallel rays. It's very similar to the idea that if you were to look at light from the sun, we know that light from the sun diverges from the sun, and the rays are divergent. But we are so far from the sun, and our size of view is so small, we treat all those rays going through a magnifying glass as being parallel. Right? They're not really parallel, but they're close to parallel. So we use a parallel approximation. We're going to consider all these 7 rays to be parallel, even though we have to keep in our mind they are converging to a distant point. Okay? They're not truly parallel. Okay? All right. So keep that in mind. So it's obvious from what we've talked about earlier that if I were to look at the spot on the screen that is directly in the middle in line with the middle of the single slit. So imagine that I have a slit that is some width d, and at the middle of the slit, I draw a perpendicular line, and I look at the intensity pattern from the slit. And this is, of course, now this is going to be an opening, which I'm going to call capital D, and of course the wavelength is still lambda, and the angle is still theta as a measurement from the central axis. Okay? All right. So, so now what I want to do is what is the intensity at theta equals 0, right here. So this is theta equals 0, right? Well, one thing I know from looking at these is that if the phase of the light was of all of these rays, if they were in phase at any instant of time, if I take a snapshot of the electric field vector, they will have the same phase everywhere along this screen, within this region, right? So the phase of this left sine wave will be the same as that one, that one, that one, that one. Therefore, they all travel the same distance, or nearly the same distance, to the distant screen, and therefore they all arrive in phase. That the phase difference of the rays from these different, the phase difference of the sine wave corresponding to these 7 rays is all 0, the phase difference. There is no phase difference. And they all add together, and I get a maximum intensity. The amplitudes are adding linearly because there is no phase difference between the different waves. Right? So at theta equals 0, I obviously will get this intensity maximum because the light from any point on that, emanating from any of the subslits within that slit will arrive in phase at point P on axis where the center of the image is. Okay? That's intensity maximum. And it's intensity maximum because all 7 of those sine waves are adding together in phase. Okay? That's intensity. All right, now, we go off a little bit. Let's look at what happens at a steeper angle theta. If I go to a steeper angle theta, and I'm going to skip this one right now. This one's a little more complicated. No, I take that back. This one's a little more complicated. Let's go to this case right here. In this case right here, I have a case where I'm at a given angle, which we define as sine theta equals lambda over d. Why lambda over d? Lambda over d is a particular case in which the path difference of the ray from the top travels an extra distance lambda compared to a ray from the bottom. So notice that the path, that the ray from the top of the slit travels a distance lambda further than a ray from the bottom of the slit. Consequently, well, we'll get to that in a second, right? I should say similarly, or by consequence, a ray at the bottom of the slit will be exactly 1/2 of a wavelength different than travel 1/2 of a wavelength longer path length or path distance at the middle point, at the middle ray of the slit than the one at the bottom. So this ray travels 1/2 a wavelength longer, and therefore 1 and 4 are arriving at distant point out of phase with each other. If the path difference is 1/2 of a wavelength, then the phase difference is 180 degrees, and the phase difference when adding 2 sine waves together that are 180 degrees apart is 0. It's a destructive interference. There's no light. Similarly, the light from 2 cancels the second ray cancels the light from 5, because if 1 and 4 are exactly 1/2 of a wavelength off from each other, then 2, with 1 and 4 are 1/2 a wavelength, then 2 and 5 are 1/2 a wavelength, 3 and 6 are 1/2 a wavelength, and pairwise they cancel. I can look at the same idea if I go to an even steeper angle over here, where now I go to an angle where sine theta is equal to 2 lambda over d. Why 2 lambda over d? Because the important thing to realize or remember is that the angle theta from the central maxima, this angle theta that we call theta of the intensity pattern, is the same theta as the opposite over the hypotenuse of this right triangle. So the opposite is lambda, the hypotenuse is d, so sine theta is lambda over d, and that's how I got this condition. Similarly, if I had that sine theta was equal to 2 times lambda over d, so in this case, the ray at the top of the slit travels a distance 2 lambda further than the ray from the bottom of the slit, then I can also find a pairwise cancellation every time I add 2 waves that are 1/2 a wavelength different from each other. So for example, this ray 1 and ray 2 are 1/2 a wavelength apart from each other, traveling that much distance further for ray 2 than ray 1, so they add to 0. Similarly, 3 and 4 add to 0. And if I did this for enough slits, I could show you that pairwise, they all cancel and add to 0. So a general condition for intensity minimum for the single slit, so now we're talking about, let's see. So now we're talking about slit, which is right here. So the general condition for minimum intensity, and I can erase this now because these are all equations for double slit, and we're moving on to what we call single slit. And so the general condition for minimum intensity is that d times sine theta is equal to m times lambda. M equals 1, 2, 3 for minimum intensity. So, for example, what that would mean in this particular case here is that this is the first intensity maximum. So, oh, I forgot the theta, right? In fact, I can actually be a little more explicit about theta. What I can do is write that this is equal to d times sine theta, and this is theta sub m minimum. Okay? So this reminds me that this angle is the mth minimum from the central axis. Mth minimum from the central axis. Okay? So this would be theta 1 min, for example. This first one would be theta 1 min, and this theta 1 min would occur when sine theta is equal to lambda, or d sine theta, or sine theta is equal to lambda divided by d. Right? Similarly, there will be another intensity minimum when, over here, when we call this sine theta 1, and sine theta 2 min will be equal to 2 lambda over d. And that would be theta 2. Right? And then theta 3 will be where the third minimum is, etc. Right? So this is the equation that actually describes it for us, at what angles from the central axis or the central maxima these minima are going to occur. And consequently, although we won't prove it here, the maxima, well, we will prove it when we finish the derivation, but the maxima occur halfway in between. So for example, sine theta 1 maximum, which is where the angle for the first fringe maxima is, will be equal to 1/2 lambda over d. And the location, this should be displaced down, so let me move this one down. Oops, no, this should be up. I'm sorry. What did I do? Yeah, that's the maximum. This one is sine theta 1, that's sine theta 2 minimum is equal to 1/2 lambda over d. And this one will be, that will be another minimum. Yep, did I do this right? I may have made a mistake. I made a mistake. This is 2 lambda, my mistake. And this one, this minimum will be at 3 lambda. And the maximum will be halfway in between. So I think I may have I've got one more mistake here, and then I will finish. Here we go. 3/2 lambda over 2. So this will be, another way of saying this is that the maximum occur at sine theta m maximum is equal to m plus 1/2 times lambda over d, and m is equal to 1, 2, 3, etc. all the way up. And similarly, for the for the minimum, there will be a similar equation. An easy way to remember this is that the maxima of the double slit is the location of the minimum of the single slit. And the minimum of the double slit is the location of the maximum of the single slit. So they're reversed. That's just an easier way of writing it. I don't need to write it out. If you just think about that, you know how it works for double slit, then you reverse it to get where the maximum and minimum are for the single slit. Okay. Is that clear? Okay. All right. So, without further ado, now once we've identified where the maximum and minimum occur, we now want to know what is the intensity everywhere in between. Everywhere in between. And that requires the same sort of analysis, which is we want to know what is the intensity as a function of theta. The intensity as a function of theta is going to be equal to some constant c times the square of the resultant electric field when I add contributions, when I add the sine waves from all subslits. From all subslits. Right? And of course, these sine waves from the subslits are going to have a different phase with respect to each other. They're going to arrive at a different point P at a slightly different phase than we expect. Then they'll have a slightly different phase with respect to each other. And we're going to calculate that in a minute. The general thing I want to point out is that you want to see what the result looks like, or an approximation result. This is the picture of the single slit intensity pattern as a function of the angle. And it's, lost my, oh, here it is. As a function of angular distance from the center of the screen. The only caveat I would point out is that these amplitudes of the maxima get smaller and smaller as you go further out, and that's not really shown here. But what is shown is that the amplitude of the maxima is definitely much smaller relative to the central maxima of the peak. Right? So that's something that you can see from this slide right away. So I'll try to do an example a little bit later, but let's move on to finish the derivation so you can do your homework problems or start working your homework problems. So the basic idea that we want to pursue in calculating this is, how do I find out what the amplitude of the sum of all these sine waves is when they arrive at a distant point P on a screen? And that's the same question that we have here, which is, what is the electric field amplitude as the result of adding all the sine waves from the different subslits? Now, keep in mind here that as I go off to a distant point P on the screen, that if I'm looking off at an angle theta, then the sine of that angle can be given by this distance divided by this distance. So this distance is d. This angle theta to the distant screen is the same as this angle theta, which is drawn perpendicular to the rays. And so d sine theta, capital D sine theta, is the path difference that the ray at the bottom of the screen takes with respect to a ray at the other end of the screen. That is the path difference between this ray number 7, and 4, 5, 6, 7, ray number 8, and ray number 1 is d sine theta. If this one takes a path difference d sine theta, then it has a phase difference of what? How do I calculate phase difference from path difference?
Times 2 pi over lambda.
2 pi over lambda, yes, thank you. If you multiply path difference by 2 pi over lambda, then you get phase difference, right? Okay? And in particular, there's one phase difference that's unique to this problem that's given a special name variable, which I call beta. Fortunately, Katz, I think, calls it alpha, but I call it beta because that's the Giancoli nomenclature. And that is that beta is equal to 2 pi over lambda is actually the phase difference between paths of rays arriving from the top of the screen compared to those arriving at the bottom, the top of the slit compared to those arriving at the top of the slit. So this becomes 2 pi over lambda times d sine theta, and this, of course, is the phase difference between the ray at the top of the screen and the one at the bottom of the screen. Okay, so let's suppose now that we divide the slit up into n subslits, and in this case, n is equal to 8, I think, if I've counted these right. There are 8 subslits for these different rays, and therefore the width of each subslit is delta y. Right? So the path difference between adjacent slits is going to be delta y times sine theta, just as the path difference from the bottom to the bottom's ray to the top ray is d sine theta. This is delta y, and in fact, delta y is n. Delta y is equal to the width of the slit divided by n, where in this case n is equal to 8. So the one that we just drawn is n equals 8. Okay, so there's a phase difference, delta beta, between adjacent rays. And that phase difference between those adjacent rays is going to be the 2 pi over lambda times the path difference between those adjacent rays. And the path difference between light arriving from a distant point P from two different adjacent rays in these subslits is delta y sine theta. So if the width of the subslit is delta y, then the difference, the path difference of the light from the second slit is going to be travel distance delta y sine theta further than light from the top slit. Therefore, it will have a longer path length, distance to reach the screen. As a result, it will arrive out of phase. And the amount by which it arrives out of phase is 2 pi over lambda times the path difference, which is delta y times sine theta. Okay? So now what we know is what is the relative phase difference of the sine waves arriving at P as we go from one subslit to the other. And that's what delta B is. And if I'm going to add them all together, then I have to add these vectors n times, and each of them will be phase shifted with respect to the other one by this quantity delta B. This is the phase difference between sine waves arriving at a distant point on the screen that travel a difference in path length given by delta y times sine theta. So how do we do this? Well, the way we do it is the same as we did for the double slit. Only in the double slit case, we only had two vectors to add up. We had the electric field from slit 1 plus the electric field from slit 2. And slit 2 had a phase difference. I mean, the light arriving from slit 2 had a phase difference, delta, compared to light arriving from slit number 1. And so we did this vectorial diagram. We said if we add the vectors, if we add the two vectors in this way, the resultant vector is the amplitude of the resultant field when both of those waves are added together. Now, instead of adding 2 waves together, we're going to add 8 waves together, or n waves together. As many subslits as I decide to make. Okay? And so, and each one is going to have a phase shift with respect to the other one of delta beta. And so, because I've divided the slit into subslits, the light intensity from each subslit gets smaller and smaller. Right? So the length of the electric field vector contribution from each subslit is very small. But if I was on the central axis and I were to add them all together, all those amplitudes together, we know that all of them are in phase at theta equals 0. We showed that in an earlier slide. So we would do the linear sum of all of the amplitudes from all the different subslits, and we should get the amplitude of the original wave, which is E. In this case, it's, I forget the actual name, I think on the screen, we'll call it E0. E0 being the amplitude from the full slit. But the point is that at theta equals 0, the amplitudes from all the subslits add up linearly, and I get a maximum intensity, and the length of the summation of all those light from all the subslits gives me this length, and that length is the amplitude of the resultant wave. And we need the amplitude of the resultant wave because what we want to find next is the intensity. And the intensity is a function of the amplitude of the resultant waves. Okay? Now, notice now if we go off at an angle theta, that now the angles of the contributions from adjacent subslits are off phase shifted by an amount delta beta, and so every time I add an element electric field from a subslit, the next one gets added inclined in an angle delta beta, another one delta beta, another one delta beta, and I do this n times because there are n subslits, and the resultant is that the vectorial sum of all of these is the arc of a curve, of the arc of a circle. And now all I have to do is find the chord length. What is the chord length of this as a function of beta? Remember? Okay? As a function of beta. And beta as a function of what angle I'm looking at on the distant screen. So, it's a chord length problem, okay? It's a chord length problem, and so the simple answer to this is what's the chord length of a arc of a circle? What is the chord length of the arc of a circle? Well, we only need probably two equations to solve this problem, and I'll put one of them up right now. So one of them is to relate to the quantities of interest. We're trying to get after E theta 0, right? As a function of, I can't spell function, as a function of the central electric field amplitude. This was the electric field at theta equals 0. And of course, we want to know it as a function of beta. Right? So what are two equations? This is the chord length. This is what we're after, right? We need this quantity because we have to calculate the intensity. And to get the intensity, we need to know what is the resultant field. Okay, so to get this, I'm going to write two equations. One is, looking at that diagram on the board, on the PowerPoint, I can write that sine of beta over 2 is equal to E theta 0 over 2 divided by the radius r of the circle. Everyone see that? Sine of beta over 2 is half of the chord length, which, by the way, this is a mistake in the slide. That should be E theta 0. That's actually the amplitude of the resultant electric field. So I take half of that width, which I call E theta 0, divided by 2. That's this half of the chord length, divided by r is the sine of beta over 2. Right? So that's one trig identity. And the other one is that I can write that the definition of an angle in radians is the chord length divided by the radius of the circle. So this becomes E0 divided by 2 divided by r. Okay? So I have two equations. I have one equation here. I have one equation here. And now I can eliminate r. So if I eliminate r from the equation, I get that E theta 0 is equal to E0 times sine of beta over 2 divided by beta over 2. Okay? And this is exactly what I want. And this now just, I'm actually just 3 minutes away from the final result. Right? Which happens to be the 3 minutes left in the class. Okay? All right. So now what I do is intensity is proportional to the square of the resultant amplitude of the electric field. So I need to use this equation, and I write that I of theta is equal to, let's put this in here, and I square it, so I get that it's equal to C times E0 squared times sine squared beta over 2 divided by beta over 2 quantity squared. Right? And that is my answer. And remember that beta is related to theta. It is equal to 2 pi over lambda times the path difference from the top of the slit to the bottom of the slit, which is d sine theta. Okay? So I now have intensity as a function of theta. I need to get rid of my constant. Right? I need to calculate something. Well, the way we do it is to say this constant is related to the intensity at the central maximum. And the central maxima occurs at theta equals 0. So let's evaluate this at theta equals 0. And at theta equals 0, it turns out that beta is equal to 0. And you may say that sine of 0 divided by 0 is indeterminate. It's 0 divided by 0. But we can do another trick, which is to use L'Hopital's rule and take the limit. We can take the limit, and the limit of what is the ratio of these two quantities as beta goes to 0. And the answer is that in the limit that beta goes to 0, that sine squared of beta over 2 divided by beta over 2 squared goes to 1 as beta or theta goes to 0. Right? So as theta goes to 0, then this whole term becomes unity. So the intensity at theta equals 0 is equal to C times E0 squared. Right? Remember, E0 is the resultant intensity at theta equals 0. Anyway, so in fact, this actually just shows you that in fact it's the case. Because I've evaluated this at theta equals 0, this term goes to 1. So now, this term right here is just, this quantity here is just the intensity at theta equals 0. So we have the same result as we had with the single slit, that the intensity as a function of theta is equal to I at theta equals 0 times sine squared beta over 2 divided by beta over 2 quantity squared. And this is the intensity for a single slit. Intensity versus theta for single slit. Okay. And that's our result. Now we'll do some examples next time, and we'll try to use this a little bit, but you've got enough information now to be doing your homework. This is almost the end of chapter 35. We've got one more section to do on, but you should have enough to start beating on the problems.